In any AC circuit, the voltage is constantly in motion, swinging from a positive peak to a negative one. So how do we pin down a single useful number to represent it? The answer lies in a really clever concept called the RMS value. So here's what we're going to cover. We'll start by looking at the basic problem with measuring AC. Then we'll define what the RMS value actually is, see how to calculate it, and check out where it's used in the real world. Finally, we'll wrap up with a quick summary. Let's get started. First things first, to really appreciate why we need the RMS value, we have to understand the fundamental challenge that it was created to solve. And this really is the central question. For any kind of practical engineering, we need a consistent value for our calculations. But the very nature of alternating current is that it's, well, always alternating. Now, if you think about direct current or DC, it's very different. DC has a steady, constant value, which makes it incredibly easy to measure. But AC, as you can see, is this continuous sine wave. It's never sitting still. So which point on that wave do we choose to represent the whole thing? So you might think, well, why don't we just take the average? That seems logical. But here's the catch. The positive half of the wave is a perfect mirror of the negative half. They completely cancel each other out. So over one full cycle, the simple average is always zero. And that can't be right, because we know AC is doing real work powering our devices. So if a simple average is useless, we need a much smarter approach. And this is where we introduce the root mean square value, or as we all call it, RMS. And this definition is the absolute key. The RMS value gives us a way to make a direct apples-to-apples comparison between AC and DC. It answers the question, what DC voltage would produce the exact same amount of heat in a component, like a resistor? This gives us a real physical way to measure the effectiveness of an AC source. All right, now that we know what it is, let's look at the formula and see how we actually calculate this for a standard AC sine wave. The formula is actually very straightforward. For a pure sine wave, the RMS voltage is simply the maximum or peak voltage, that's Vmax, divided by the square root of 2. And you know what? The exact same relationship works for current, too. Now here's a handy number to remember. 1 divided by the square root of 2 is about 0.707. This means the RMS value of a sine wave is always about 70.7% of its peak value. And here's where it gets really interesting in a practical sense. Let's take a standard household supply, say 230 volts. That 230 V is an RMS value. So if we rearrange our formula to find the peak voltage, we just multiply 230 by the square root of 2. And look at that. The voltage coming out of your wall is actually peaking at around 325 volts, dozens of times every single second. Okay, so we know how to calculate it, but why is the specific value so important? Why is it the standard for pretty much all AC applications? Well, for engineers, the RMS value is everything. It's the foundation for voltage ratings, it's absolutely essential for calculating power correctly, and it basically dictates how almost all AC equipment is designed and specified. And this is probably the single most important thing to remember. When you look at an appliance or the specs for an outlet and you see an AC voltage rating, that number is the RMS value. It's the universal standard. All right, let's do a quick recap of the most important points before we finish up. So just remember these 4 key things. 1, the simple average of AC is 0, which is why we can't use it. 2, RMS is the effective DC equivalent and it's based on heating effect. 3, the formula is the peak value divided by the square root of 2. And 4, that voltage number you always see, like 230 volts, that's the RMS value. So now that we have a solid way to measure AC voltage and current, the next logical question is, how efficiently is that power actually being used? And that leads us perfectly into our next topic, power factor, which is the key to unlocking efficiency in AC circuits.